Hi everyone, thank you so much for joining today's London Java community event. For those of you who don't know me, my name is Abby. I work with Barry Cranford, who's the founder of the LJC, and I have the privilege of welcoming you to today's event. The LJC is just one of the communities that is run by RecWorks. We're a tech recruitment company with a massive difference. As a company, we believe that recruitment really can be a force for good in the industry beyond just placing people in jobs. We have a particular focus on learning, mentoring, and personal development. From our perspective, if people want to learn and others want to teach or share their knowledge, we are more than happy to connect you through our communities and events. We see this as giving back to those we've worked with in the past, but also paying it forward to those we hope to work with in the future. To date, we have run over 700 events for engineers, developers, students, graduates, CTOs. We have run conferences, lightning talks, hackathons, all sorts. In January of this year, we made our 4,000th introduction through our Meet a Mentor program. We are really excited about that and looking forward to seeing where that's going to go next. As I've already said, we love to give opportunities for people to connect, and this event is part of that. If you would like to know more about our other communities, please do get in touch with myself or Barry and we can take it from there. And finally, just to let you know, the recording of today's session will be available on YouTube. I will put the link to our channel in the chat, or you can message me as well, and I can send it over to you when it's ready. If you have any questions while Martijn is talking, please do put them in the chat as we go along, and he will be able to have a look at those and see what he can answer along the way. So without any further ado, let me hand over to Martijn for the Diabolical Developer. Over to you.
I think you're on mute there, Martijn.
All right, bonus points. First points for being on mute. Well done, me. Hi everyone, nice to see you all. Good to see some familiar faces and some new ones as well. For those who don't know me, my name is Martijn Verberg. These days, I am a principal group manager for the Java engineering group at Microsoft. Yes, you heard that right. That basically means I'm a manager of managers, which also means that some of the technical detail you see in this presentation was very helpfully put together by some of my engineering group and other friends in the industry, like Ben Evans and Jason Clark from New Relic. Jason Clark from New Relic, Ben Evans is now at Red Hat, and some others as well. But I will do my level best to answer any technical questions that you have. I still learn some of this stuff through osmosis, but if I get stuck, then I will make sure that one of my engineers can get back to you. I help run the London Java user group. I help co-found Adopt OpenJDK, otherwise known as Eclipse Adopt Team these days, and I generally cause trouble in the industry, hence my nickname. So today we will cover some of the fun research that Microsoft has done over the past year in looking at how JVMs run inside containers. And there's lots of reasons for this, which I'll get into. And again, it's thanks to Ben, Jason, Monica, and Kirk, and my partner in crime, Bruno, at Microsoft, for helping put together this talk. Alrighty. So this is what I'll cover. First of all, I'm going to talk a little bit about how Java is run at Microsoft. Again, it's a little bit of a surprise when people hear this, but we actually use a ton of Java inside Microsoft. And so we have a great deal of interest in reducing our costs and making sure we're as green as possible when we run out of Java. That's kind of part of the driver here for all this work. Then I'll dive into some of the basic JVM ergonomics, some of the things around garbage collectors and how that works inside containers. And then some of our recommended starting points. And we're not going to say that this is perfect for your particular application, but it is a guide if you're absolutely stuck on, what to start with, especially if you're doing a migration or a greenfield. All right, so Java at Microsoft. Promises won't be marketing, at least not too much. So we actually have over 2 million JVMs in production at Microsoft, and that is just for Microsoft and its subsidiaries itself. So these are not our third-party customer workloads that run on Azure, of which there are many millions more, but we have about 2 million that we run internally. And this surprises a lot of people, but if you look at the subsidiaries that we have in particular, such as LinkedIn, good old Minecraft, which we very helpfully managed to get to Java 17 last year, so the excitement of all the mod community there, and Yammer as well, of course. But also in particular on Azure, we have a bunch of big data services, and they will run things like Apache Spark, Apache Accumulo, NiFi, Kafka. Like if it's an Apache project, we run it as a service basically. So as you can imagine, running at that sort of a scale, you know, we call ourselves a public cloud or a hypercloud like AWS or GCP and others. Means that we really have the ability to statistically look at how JVMs are run across workloads. And we can therefore extract some commonalities, some configurations, some metrics and analysis on what may and may not work with, in particular, in this case, with containers. So there you go, Microsoft Java. It's actually a real thing. So Microsoft and myself personally are very concerned about climate change, and in particular data center impact on that. I think, can't remember the stats I saw last time, but it's something like the 7th or 8th highest electricity producer in the world, if you counted it as a country, are all the data centers around the world. At Microsoft, we have, I think, 55 or 56 data center regions these days. Can't remember exactly how many, but in and around that. And so, we appreciate, we unfortunately add to that challenge for the world. So one of the things we want to look at is, hey, can we run our workloads more efficiently and actually reduce some of that power cost? So our target, and so my personal target that I've been handed down by my senior leadership is by 2030 that we must be getting to carbon neutral and inevitably carbon negative. So that's the goal. And one of the things we've certainly discovered with Java and JVMs in particular, and the way they run, is that they often don't run terribly efficiently in containers out of the box. And so there's a lot of overutilized memory or CPU for bad reasons, right? Which is all very unnecessary. So that's what we'll try and cover off today. All right, so I'm going to set the stage here a little bit and just remind people about what the stack of a modern cloud typically looks like and how everything is still actually just a hardware resource at the end of the day. This is really, really important to remember. So if you're going to pick a cloud, of course, we'd love you to pick ours. That's my marketing slide. There you go. All right. But in a data center, and this is actually a picture of one of our Azure data centers, and as you can see, it's very pretty, and the cables are all neatly tidied away, unlike the data rooms you may have seen previously, or the box under your desk. But the key thing to remember is that, this is what is actually really under the hood of so-called, magic cloud compute, and magic cloud memory, and magic cloud networking. It's just a bunch of physical machines, all with resource constraints, just all hooked up together. So one of the things you really need to appreciate is, okay, which one of these hardware boxes or cluster of hardware boxes am I really running on? And how does that impact all of the virtual layers above it? So the hypervisors, the container management, the containers themselves, the operating system, so on and so forth. So pro tip number one, make sure that you, your SREs, or the folks who are deploying to your production, know exactly what SKU you're on. SKU stands for stock keeping unit, by the way. That's kind of the thing. If you go to AWS or Azure or something, it's the unit, the VM, or the cluster that you're picking. All right. So this is one iteration of what a typical cloud stack looks like. This is not every typical cloud stack. This is just one of many iterations that's now being put on offer by the various cloud vendors. So, this is sort of subject to change. But as you can see, there is a ton of virtualization going on before you even get to your JVM. All right, and remember there's that bare metal at the bottom. And that bare metal will have a certain amount of CPU capacity, certain amount of memory capacity, certain amount of hard disk networking, all that good stuff, right? So the host operating system is typically a very, very thin layer, almost always Linux, although on some clouds you may find some Windows. You also then will have a hypervisor, and the hypervisor is there to allow you to create virtual machines. So when you go to AWS or Azure or Google Cloud and you say, I want to pick a VM, it's typically a hypervisor which is serving that up for you and managing that for you. Now, the host OS and the hypervisors, these days, they are highly optimized pieces of software. So much so that, they really typically these days have a minimal overhead on top of that bare metal. That said, you should still think to yourself, hey, some of that memory, some of that CPU that's on the bare metal, which I've, in theory purchased, is actually being utilized by those two layers permanently. So my JVM isn't going to get all of that. Then inside the VM, you will have a guest operating system, typically Linux these days. And if you're running containers and it's a slightly more modern cloud offering, you're probably going to have a container engine sitting on top of that, which will then allow you to actually run containers. And obviously that's typically Docker these days, which kind of won the container war. And orchestration is typically done by Kubernetes, who won the orchestration war more or less. Then you finally have your last layer of abstraction, the JVM, which itself is kind of a black box to the operating system or to the container in terms of it understanding what is in that process, right? And so again, as you can see, you've got all of these layers all taking away bits and pieces of that bare metal resource. And so one of the things you have to understand is that, for example, if your container says, hey, I'm giving you 4 gig of memory, you can't then just go and throw a 4 gig heap at it, right? Because the operating system or the bits of the operating system that will run inside that container, usually, again, a Linux, maybe Alpine or Ubuntu or something, they need some native memory to operate, right? The JVM itself needs some native memory to operate. Maybe you've got another process or small process or two like gRPC or something running in that container, and that also takes a little bit as well. All right. So I pretty much covered all this, so you'll be able to get the slides after this to have a look at some of this in detail. But again, it's important to remember, what is the bare metal host that I'm getting? For many of you, if you are truly running on a virtual machine, you can almost treat that as the true resource that you're getting and sort of start from there. All right. Some more modern cloud stacks just offer purely containers these days. So they remove the they remove the hypervisor, they remove the concept of VMs, and the host operating system just purely hosts container engines, and the only thing that's surfaced to you are containers. This is becoming increasingly popular for people who are running true container-only workloads, and you'll see behind the scenes that a number of what we call function as a service type offerings are also starting to be run in this way. So this reduces some of the overhead, some of the resource ask on top of that bare metal, and allows people to pack in, more containers, and you get more security, more isolation, all that kind of good stuff. So again, it's worth checking with your cloud provider or your data center provider. What is it you're getting? What does your stack look like? All right, pretty much covered all that. All right, so this is the only thing I ask you to take away. The number of times we have seen internal and external customers do things like, cool, I'm on my own data center in my big bank, and I've got a bare metal machine with 32 gig of RAM, and I decide to give it 8 VMs with 8 gigs of RAM each. And 64 does not go into 32, no matter how clever the hypervisor is. Now, hypervisors and VMs are very clever at sharing resource, but if you have any of those VMs that are at max capacity in terms of using the memory, you're just going to start having to hit paging, right? And so instead, memory from the hard disk will be used to try and make up for the loss, and you're going to have a really bad experience. So we see lots of customers do this. So please do go back and do your basic arithmetic and make sure that the number of VMs or the size of the containers you're squeezing into your VM, all those good things, make sure the basic arithmetic works. And if in doubt, also leave yourself a little bit of headroom in each case as well. Same tip goes for applications that you might be deploying to larger multi-core machines. If your application is kind of single-threaded or single-threaded in a lot of places, you can buy the biggest 64, 128 core machine that you like, and your app just isn't going to go any faster, right? So something else that's worth checking before you go and just buy new hardware or rent that larger VM on the cloud. Make sure that your application can actually take advantage of the parallelism on offer. Good old Amdahl's law at play there. All right, so that's my math reminder, and then on to the actual fun part, the ergonomics. So one of the challenges we see with a lot of folks is they do their development on their desktop, and maybe they're a little bit on the leading edge, and they've got a really powerful Apple laptop or the latest Linux beast mode things, and so they do run containers and they do run Kubernetes on their desktop or laptop, and everything looks fine, right? The challenge is that the JVM and the way it looks at ergonomics is very different when it's inside a container than it is on your host operating system. So if you're testing and thinking that the JVM is going to behave in one way on your laptop, and as soon as you deploy to production, especially inside containers, you're potentially going to get something different. All right, that's my magic empty slide for no reason. Here we go. So we went and asked some questions on Twitter, because we all have Twitter, and it'll be interesting to see what Elon does to it if he buys it. But for now, polls are still allowed. So we ask folks out there randomly, like, how many garbage collectors do you think there actually are? And about half of the audience got it right. So that already tells us that half of Java developers, or people who perhaps deploy Java, actually don't understand what the JVM has to offer them as per Java 11 onwards. So that's a little concern already. Then, do you expect the JVM just to choose the right garbage collector based on some ergonomics? And most people think, yeah, it does. And that is mostly true, but it doesn't pick as cleverly as you think it might. And so that's the big warning. I'll dig into that in a second. How many GCs do you think the JVM actually evaluates when doing these ergonomics? And this is where people got it horribly wrong. So that second answer, the 25% one, is actually the correct answer. But most folks incorrectly think that it chooses between 3 or all of them, or they actually just don't know. All right, so the point of this talk is to help you understand what the actual truth is and how you can go look at this yourself. All right. And do you trust the JVM ergonomics to pick the best GC for you? And there's just too much trust in the JVM. We know it's amazing, we know it's wonderful, but I will tell you now, you actually can't trust it. So you're gonna have to start looking at this stuff yourself in detail. Most people would like better JVM ergonomics, and that is something that Microsoft and Oracle and Red Hat and AWS and a whole bunch of other vendors are starting to look pretty deeply into. And already in Java 19, there's a bunch of new ergonomics work happening, which is good. And we're doing a bunch of research to go and add more. All right, just checking chat. There's nothing extra there, it's fine. Okay. So here's another survey that was done. And it was discovered that most developers are deploying Java workloads or JVM workloads up to 4 CPUs. You see that 2 CPUs actually, or 1 and 2 CPUs kind of dominate even that up to 4 number. Up to 4 gig of RAM, and they're pretty IO intensive, right? And the IO intensity either comes from like dumping a bunch of logging to disk, or shunting a bunch of big data across the network with JVS queues or gRPC or RESTful web services or something of that nature, right? Java apps tend to be big, heavy, enterprisey data apps. That's pretty common use case. All right, so we worked with our friends at New Relic. They recently put out a survey with where they analyzed over 10 million production JVMs. And they discovered a majority of them are just run with 1 CPU. The majority of them are actually running at a gig of less or RAM. and a majority of them do not have their GC explicitly configured. And so it's just up to the JVM to decide. And so what they tend to see is a lot of their customer deployments where they see their customers just randomly trying things when the performance of that JVM isn't doing what they want. And you'll see people, either increase the heap size, add more replicates, so scale out, or just give up on Java and say, we don't understand this, and we're going to rewrite the whole thing in Node.js, which I would definitely not recommend. That is not the way forward. The better thing to do is just to actually understand how the ergonomics work and just apply some common sense configuration parameters. So this is how the JVM currently selects its ergonomics. We focus on, hopefully everyone's on Java 11. You can put in chat if you're still stuck on Java 8, and everyone can call shame on you. A quick note on that: if you have a reluctant boss or bosses that will not move off Java 8 for whatever reason, feel free to contact me directly, and I'll happily have a chat to them and walk them through some of the very large migrations we've done at Microsoft. We've got the entire fleet on Java 11 or 17 for those 2 million JVMs. And it has absolutely been worth it in terms of developer productivity, reduction of the running those 2 million JVMs, and very often double-digit percentage increases in latency and throughput performance statistics. So it's absolutely worth the cost of doing it. Right, for Java 11 or later, the ergonomics will either pick the serial GC or the G1 GC. And that's it, right? And of course, with 11, you've also got choices like Shenandoah, you've got Parallel, you've got CMS. I'm probably missing one or two, but the ergonomics will only look at 2 of these. And for Java 8, it's serial or parallel. So the default GC that gets chosen if your memory is less than that strange number of 1,791 megabytes is going to be the serial GC. Otherwise, for Java 11, it's going to pick the G1 GC. So that's something that you're going to have to think about. And instead of perhaps letting the JVM set this implicitly, that you actually want to go and set this explicitly. That's tip number 1. All right, time for a little demo. Let's see if I can get this to work. So I'm just going to escape out of here. Oops. And I'm going to swap to, let's see if this works. Now, I'll just ask, I can't see people's faces, so can someone tell me in chat if they can see a Visual Studio Code editor there? Yes, excellent, thank you. All right, so naturally I'm using Visual Studio Code, which I'm not going to say is a replacement for IntelliJ IDEA, I should say, because I use IntelliJ as well, but it's a great for a lightweight code editor, even with Java. And so I use it quite often when I'm doing little snippets like this. So what I'm going to do is try and write some code here to detect how many processes I've actually got. And look, GitHub Copilot, which I'm attached to, has actually decided to go and figure out exactly what I need to write. So for those of you who don't know, GitHub Copilot is a sort of machine learning AI-assisted coding service. And it's kind of magical. It basically has scanned lots of GitHub repos and sort of picks out what it thinks would be the most common thing that you want to write next. So probably by 2050, we'll all be out of a job. Unfortunately, the machines will just write all our code for us. So I'm just going to tab complete that and let that go. And then I'll want to print out that result. And as you can see, GitHub Copilot, having read the line before and having scanned other code previously, knows exactly what to go right. Voila, so I don't need to do any of that. And I'm going to run this using the Microsoft build of OpenJDK, because we have one of those ourselves. And for those of you who are running on Azure, the Microsoft build of OpenJDK is the one you want to use, because my group builds, runs, and supports that, and we give you support for free on Azure. So as you can tell here, it's returned that I have 16 available processes on my lovely MacBook Pro here. But this is the sort of code you also want to run in your container and make sure you understand how many processes Java thinks the container is giving it. That's really critical. All right. The other thing I was going to show you quickly was the picking of the GC. Let me have a look here. Right, so I've got a little bit of code here. This is a little shell script which just runs some Docker. As you can see here, I've set the CPUs to be 2, but I've set the memory to be 1500 megabytes. Right, and if you remember that if I'm below 1791, it should select the serial collector. Yeah, I'm going to grab myself a base image from Microsoft's container registry, which has got the Java 17 JDK pre-installed on Ubuntu, and I'm going to print out all of the flags that the JVM has set implicitly. And this is a really cool thing to check. So the JVM implicitly, through its ergonomics, sets a whole ton of flags. And if you use this particular setting, you can actually see what they all are as a default. It's something that not a lot of folks use. And I'm just gripping for like which GC we're going to be using here. All right, so I just run that here, and hopefully this shell is large enough. As you can notice, I still pretend to be a hacker, so I use a nice green font. Very important, especially if you're in a cafe. And as you can see, this here Boolean here, use serial GC, has been set to true. And it's been set by ergonomics. Yeah. So even though I've got 2 processes, because I have less than that 1791, it is selecting the serial GC for me, which may not be the GC that you want. So again, it's a little bit of code that you can grab and check for yourself. So print flags final is the one you want. That one there. All right, back to the presentation. Cool, on to some information about the garbage collectors. So here is a rough guide of what we've discovered at Microsoft, and this may not be true for everyone, but a rough guide as to, hey, what's the type of workload that you have, which is the best for section at the bottom there, and which garbage collector you might just want to try first before tuning and tweaking and trying others. So as you can see, for really small single core small heaps, serial is great. That's fantastic. If you have multi-core but a small heap, then parallel is a great option. If you need to have a GC which is fairly responsive and medium to large size heaps, so we say 4 to like 32 gigs, something along those lines. Good old typical web applications are pretty common for this. Then G1 is a good choice. And if you are really extreme and you want that low latency guarantee, G1 tries its best to give you a low latency guarantee, but nothing compared to say ZGC or Shenandoah, which really do flatten out those latency bumps that you get from the stop the world garbage collector. G1 GC will cost you a little bit of throughput, right? As you can see there, the overhead there is moderate, because it sometimes will preemptively garbage collect to try and meet that latency goal. And ZGC and Shenandoah do that even more so, right? So they actually work pretty hard behind the scenes to give you that latency guarantee. But that means the garbage collector is constantly working in the background, just doing little bits of work all of the time. And so you may find that your overall throughput, so basically the number of business transactions or transactions you complete per time unit, let's say per second, will decrease slightly, but you won't get those latency or those pause spikes. So you just have to choose the one that's most appropriate for you. All right, hopefully that made sense. And again, you'll be able to catch these slides afterwards. I'll send them out. All right, so there's a whole bunch of information here because I work for Microsoft and it's PowerPoint, and so I like having lots of bullets. But really, the bottom right-hand side there is a thing you should really be thinking about. So just going -XMX or setting the RAM percentage is just not enough, especially in a container. You want to understand the type of workload you have. You want to explicitly select your garbage collector, and we really do recommend that. And that you also have enough CPUs, and I'll let you know what I mean by CPUs in regards to Kubernetes in a little bit as well. So that's all the things that you should really be thinking about. And tuning the GC is, it seems like some sort of magic science or magic art. It really isn't. Just by starting with some of those sensible defaults, it's pretty easy to do. All right, so some more default ergonomics. So I've talked before about which GC it picks. If you don't explicitly set the memory -XMX or -RAM percentage, the JVM will give you a heap size based on its own default ergonomics. So inside containers, it starts with a quarter of the available memory, which is quite small. And outside containers, it's only 1/64th of the available memory. So again, don't let the JVM just decide for you. You need to set it explicitly. What should you set it to? So our recommendation in containers is that you should set the size of your heap to be about 75%, and this is conservative, of your container memory. And the reason why we say this is because you need to give yourself enough headroom for the native portion of the native memory portion of the JVM to operate and run, plus any other native memory stuff that's going on inside that container, whether it be the little bit of an operating system overhead or other things you might be running. What I will say is that the larger your container and the larger your heap, the higher your percentage can typically go, because especially the operating system overhead and even some of Java's native memory usage and overhead, it is actually kind of a set value, right? It doesn't necessarily scale with the size of the container memory. So, you know, if you're going like 8 gig plus, I would say, or 8 gig, I would say you can probably get away with 80%. Then if you hit sort of 32 or 64 gig, you can probably get away with 85%. You just have to wait and see. You just have to, you know, check against what you've got inside, what your workload is like. There is, of course, a huge warning label here. If you are using any sort of framework, and this includes a number of the big data frameworks, they use a larger amount of native memory than your typical Java application. I'll put it that way. There is a flag, which I will send out after this because I forgot to put it in the slides, where you can track the native memory usage that your JVM has. And so you'll be able to actually measure that and at least set your limits accordingly. So you can either set -XMX or you can set -XX max RAM percentage, which is what people typically use if they're allowing, especially Kubernetes and other container management technologies, to determine what the size of the container is. All right. Hopefully that all made sense to people. Okay, so nice quote from Monica there. We just try and move this little stuff with little as possible so we don't disturb all the memory that's lying underneath. I think I've covered all of this. Yes, we've talked through all that. It's really just duplicated data. And now we'll talk about something that doesn't work so well, Java on Kubernetes. So I was going to do a demo on Kubernetes, and then I sort of started listing all the basic Kubernetes and Docker commands to try and figure out how to do that live off my laptop. And as you can see, by the sheer amount of commands and things, I just decided, nope, not going to bother with that. This is why we have managed Kubernetes services these days. It's just a whole different ballgame and things to go away and learn. Some would say that Kubernetes is a swear word in Klingon. I happen to agree with that sentiment. Once you have actually spent some time doing all of this and understanding Kubernetes a little bit better and researching how Java runs on it, you eventually come out with some information like this. So Kubernetes gives you a time slice of CPU time. Okay, so you have to do away with the concept of that, you know, you're going to get a whole processor or two whole processor or virtual processors even, or cores. It really is a time slice. So it's how many, it's based on what they call millicores. And as you can see, if you overspend your time budget, you then have to go and wait. You get throttled. You have to go and wait till the next time slice is made available to you. Now, of course, we have the JVM, which is multi-threaded, right? You're running all of your main application threads, so what we call your mutator threads. You have the just-in-time compiler thread, you have garbage collection threads, you have all sorts of other threads that are running, database connection pools, so on and so forth. So there's going to be a lot of threads contending for time slices that Kubernetes is making available to your container. So this is just something you've got to really keep in your head. And so I'll show you a little bit of math and how this can work out in your disfavor. So this is going to be a little PowerPoint animated series here. So a special thanks to Bruno. People who are in product management know how to make really nice slides, like us engineers. All right, so we have a whole bunch of HTTP requests coming in. All right. Don't move my chat window so I can talk to this properly. All right. And each request takes 200 millicores of time, right? And so 2 times 4 is 800, so just keep that in your head. 800 millicores used, we have 200 left to go of the time slice. Then we have some GC activity. And that GC work took a total of 200 millicores as well. So how much do we have left? We have 0 left, 0 time left in that particular time slice. So what happens when the next 2 HTTP requests come in is Kubernetes goes, nope, you've used up all of your allocated millicore for that cycle. Back out you go. You're going to get throttled, right? And so those requests won't be processed for another however many time. And if you're using the completely fair scheduler on Linux, which is the most bravely named piece of software I've heard of in a long time. There's a super seriously confident engineer who named that, being completely fair. You have to wait for 60 milliseconds till you come back. The other challenge with Kubernetes is the way that Java interprets these millicores or these slices. And if it's up to 1000, the JVM will think there's one processor in place. If the JVM between 1000 and 2000, there's 2 processors, so on and so forth. Now, as you know, the garbage collector, most of the garbage collectors that you want to use anyway, unless you're using serial, you want to actually be running these concurrently, right? You want the GC to be able to run whilst your application threads are still running and use up the time slices that way. However, if you've limited if the JVM thinks it's only got one processor, one core, its ergonomics won't let you do that properly. So that flag of the active processor count is something you want to set explicitly. And typically, even if you're only got 1000 millicores, typically you want to actually set that to 2 or more. That will allow you to use G1GC or the parallel collector, if that's the most appropriate one, at the same time as your application threads continue to do work without the JVM artificially stopping you. Will one day the JVM speak the language of millicores and time slices natively? I hope so. And I think that's going to be some interesting research work that's going to happen going forward. All right. Oh, not going to forward. Try this again. There we go. All right. So what we did after doing a lot of research on those 2 million JVMs that we run internally and talk to other folks is we have some default starting points, some recommended starting points for you in terms of picking how many processes you should tell the JVM you have, which garbage collector you should have, and all depending on how many CPU limits that your Kubernetes has given you. So this is a decision tree that you can follow. So maybe you want to screenshot this. And again, the disclaimer here is this may not be right for your particular workload, but we found that this is the better starting point for all of the workloads that we're running internally at Microsoft anyway. And as you can see, you'll recognize some of the things I talked about earlier. So, set the processor count to 2 if you've got 1000 millis or millicores or less. If you've got a small JVM heap, set that heap size to be 75% of the container, but then you could increase that percentage if your heap gets larger. And depending on how large your heap is, there is sort of a default garbage collector, which is typically the best choice here. And yes, the one on the bottom there, people running 32 gig containers or more, that is definitely a thing, believe it or not. We see lots of big data workloads still choosing container technology because they can scale out more easily. But each individual data processing node itself is still very, very large. Those are fun clusters to manage. All right. This graph is probably not going to be that helpful because there's a better explanation here. So one of the things we've looked at is, hey, should you go and pack fewer containers in each VM or each piece of bare metal that you have, or should you pack in lots and lots of JVMs in one giant VM or container? And the answer is, as always with computer science and things, is it depends. So here is an example of using K8s, that's our Azure Kubernetes service, where there are 6 underlying VMs. There's 4 containers running on each VM effectively. There's a controller plus 3 client nodes where the actual work is happening. And we've picked a particular SKU, and each JVM is, it's been given 1 virtual CPU, so 1,000 millicores, 2 gig of RAM, and you can see there the total amount of resources that gets utilized. And note there that the ergonomics, if we don't set it explicitly, will choose the serial GC, right? And you're going to see quite a lot of throttling on each JVM because we're only giving it 1,000 millicores. You're probably going to see quite a lot of stop the world GC because of this. And so, you've potentially got some runtime concerns there. So that's if you go wide, but short. And you see the cost estimate there that we have in K8s as it stands today with the Cost Explorer. Alternatively, you could stack them up really high. So go for a larger SKU. Notice that the cost is the same, at least the way that it works on the Azure cloud. Other clouds may vary, so you'd have to check your appropriate Cost Explorer for that. So we've got just as many JVMs doing work, so to speak. But you can see here that we're actually able to change the size of the JVMs. So on this previous one, we had 18 virtual CPUs being used. On this one, we have 12 virtual CPUs being used, less RAM. We're able to use a G1 GC, and we're actually going to get better out of the box default behavior. So because the JVM with its, you think of it this way, because the JVM with its default ergonomics was designed for the monolithic application in the big data center age, replicating at least that as a minimal set of behavior, so giving it 2 active processes, giving it enough RAM for it to actually work efficiently, it's still highly recommended even inside containers. And the way you can save costs is by stacking them up inside a single VM like this. So just a consideration that instead of necessarily going short and wide, that you may want to go skinny and tall instead. All right. Hopefully that made sense. I can't see faces, so I don't know if you're confused or not. You have to tell me in chat. Cool. So yeah, so you've got 2 types of topology. It really depends on what type of application you're running. Topology A, smaller JVMs, lots and lots of replicas spanning out. This is brilliant for tiny microservices where the service does one really small thing and does it well, and you might need 10,000 of them to respond to something. Think of how some of the Twitter architecture works as an example. And then you got the other topology where you actually have less replicas and larger JVMs in each. So typical data processing type applications, the Kafkas and that kind of thing. Cool. So as a bit of a conclusion, you really need to understand your tech stack. Even if you're on a cloud, it's not just magic resource for free. You really want to understand those JVM ergonomics, and I showed you a couple of snippets of code on how you can go do that yourself, and there's plenty of extra information on Stack Overflow, or you can just ping me on Twitter. Understanding the basic characteristics of the garbage collectors is really important, and selecting explicitly which GC to use depending on your container size is super important, otherwise Java will run terribly. You can do this in a data-driven manner, so you can use things like using the JDK flight recorder. We have a Java flight recorder streaming library if you're using an older version of Java. We can stream that data and look at it in Java Mission Control. You can look at the GC logs. We have on GitHub a toolkit called GC Toolkit, which can help you parse those logs, turn them into a model, and then you can analyze those models. And if you do those two things, you'll be able to run Java far, far more efficiently than you possibly are at the moment. All right. Scaling out is not necessarily the silver bullet for Java, right? So you really need to understand what your workload needs on an individual JVM unit of work. And often at least 2 processors and at least 2 to 4 gig of RAM is where the JVM is typically happiest. Again, it really does depend on your workload, so do think that through. Avoid the JVM ergonomics by default. Always set your GC and the number of processors and the heap size explicitly. And then make sure that you analyze GC logs or JDK flight recorder data so you really understand what is actually going on instead of just guessing and saying, oh, we need to increase the heap, or we need to scale out by another 10 pods or something. And that's it. If you want to learn more in real deep dive technical detail, the Well-Grounded Java Developer 2nd edition, which Ben Evans and Jason Clark have authored. My name is on there, but I literally contributed an appendix and half a chapter. So they're very kind to add me there. But that has a chapter 12. It's in the early access program, so you can even see that for free at the moment, I believe, which really does a deep dive into all this detail about how to run Java effectively inside containers and inside Kubernetes. So if you want the deep dive detail, a lot of that information is in there. And at Microsoft, we've also published the material that I've just presented to you as guidance and full documentation. And that's free for anyone just to click on and go and see. And you'll see a whole bunch of other Java-related articles like, hey, this is why your boss should move from Java 8 to Java 11, and hey, this is how you go and do it. So you can definitely go to that location and get all that free advice. All right, with that, I will say a big thank you, and we'll happily take any questions. All right.
That was fab, Martijn. Thank you so much. For anyone who wasn't here at the very start, I have put the link for the recording in the chat as well. So our YouTube channel is there, or message me, that's fine. Did anybody have any questions? Oh, yeah, something in the chat. Martijn, how much, if any, is JVM ergonomics turning dependent on the hypervisor and host OS? And second question, what's the host OS on Azure? Does that make sense to you? I hope it does.
It does. So on the first question, so the host operating system and the hypervisor has very little to do with the JVM ergonomics. In fact, it has none. The JVM ergonomics will look at what the guest operating system is giving it, or what the container is giving it. So the JVM isn't typically digging into or understanding what the hypervisor or what the host underlying host operating system is doing, and that's by design. That would probably be a bit of a security challenge, to put it mildly, if managed runtimes were allowed to go dig into underlying layers like that. What is the host operating system running on Azure? I will just say that it varies, and we'll leave it at that. I'm unable to comment on that further, I'm afraid.
We've got another question in the chat. The recommendation seems to be to avoid JVM on, I'm no good at symbols, which way is that? Less than 2 gig on K8s. Is that right?
So what I would say is that if you're on Kubernetes, if you're less than 2 gig of RAM, you really want to have a workload which is, doing a minimum amount of work. So really a true microservice, almost a function as a service. If you have your typical application, which might be opening up, a HTTP connection pool of 10 and a database connection pool of 10, and you're therefore going to be also manipulating a lot of data inside that JVM, less than 2 gig just isn't going to work very well for you. And again, the garbage collector is probably going to default to serial if you're below that 1791 mark, and that's going to effectively pause your JVM a lot inside that container, especially if it starts using up the millicores.
Hi, Martin. I have a question. It seems like all of these numbers are when Java runs in a JVM. Do you got any experiences or recommendations for running native/static Java, where through a framework and GraalVM you compile Java into a native executable?
Yeah, so running Graal is becoming, I wouldn't say more popular, but a lot more people are experimenting with it, right? In particular because it has better startup time guarantees than OpenJDK has today. So I think with GraalVM or into any sort of native image, my advice there is that you need to do the same thing as I recommended with in terms of tracking your memory usage inside the container. So you need to understand, you need to effectively run that native image, throw load at it, traffic for 24 hours or however long your application cycle goes for, and just measure using whatever standard operating system tools for tracking your native memory, and see, okay, how large does the native memory of that particular GraalVM process take, right? Because it's one single large process again. And again, you'll need to make sure that you're giving it, that 20 to 25% headroom for everything else that's happening in that container, and that should work fine. GraalVM Community Edition has some serious catching up to do in terms of its capability for garbage collecting. It is not great performance, to put it mildly. And so in our experiments, and I don't have full data to share yet, but in our experiments, as soon as you have a truly long-running GraalVM service, so if you're really using GraalVM to replace OpenJDK for a typical web app, for example, that performance will start to degrade heavily over time. It looks great to start with because it's really fast to start up and things, but then without having the C2 JIT compiler and to dynamically optimize the applications that are going, and without the more modern GCs that OpenJDK has, the Community Edition just doesn't quite cut it. I can't comment on the Graal Enterprise Edition. I can only assume it operates much better. But you do have to pay Oracle a commercial fee for the rights to go and run that thing.
Just a quick follow-up question. Thank you for that. The idea behind GraalVM or native/static Java is that you need less resources. So from your perspective as a cloud provider, it could mean that if everybody uses native static Java and it works good enough, then that means, you would lease less hardware to serve these customers, right? So is that something that you would rather do, that you need less hardware, or would you rather prefer as a cloud provider, if you can divulge that, to say, hey, we rather let you guys stay on the JVM, then we charge everybody more, but we also need more hardware to service all these customers?
Yeah, so I can definitely state that Microsoft's philosophy is that we would love to minimize the impact of any managed runtime that includes .NET, Python, Ruby, Java, whatever, on our cloud. We certainly don't believe in encouraging people to run oversized runtimes just so we can charge them a little bit more compute. That actually, economically, it actually damages our business. So if you look at the behind the scenes costs, and also, we do have this, kind of, I wouldn't say mandate, but I think we do this moral obligation to actually reduce the amount of, power usage and hardware usage and stuff across the planet, right? So we do think about it very seriously. I would say that with modern Java 11+, I would highly encourage everyone to look at JLink and JPackage, and I see that Stephen has actually also added this in the chat. You can get a JLink JPackage OpenJDK runtime with your application code down to like, 50 to 100 megabyte in size. If you're doing a microservice, it is tiny. And so you can run these things in very, very small containers if you so choose. Now that goes back to what I was talking about with Kubernetes, and the ergonomics don't work well under 2 gig. Well, if you're running a true microservice, you can really run that in a 256 meg heap. You can, or even smaller actually. You can choose a serial collector or even the epsilon collector, which is a 0 GC collector that does nothing. If you know your microservice is going to sit there for a short time. So modern Java, if people use the right packaging tools, and I will say they're not the easiest tools to use quite yet, right? You do have to really understand how that all works on the command line and read up the documentation. There's no really nice Maven or Gradle tooling for it just yet. That is what we recommend for our customers today. If customers want to bring GraalVM to Azure, we absolutely happily allow them to bring it, and we will support them as best we can. Yeah, we feel that, I think with the changes coming into OpenJDK, that some of the benefits of going native with GraalVM will be reduced, right? You're going to see better startup time. You're going to see smaller workloads with Valhalla and things like that coming in. So I suspect OpenJDK will close the gap somewhat. That was a long-winded answer, sorry.
Fantastic. Any last questions for Martijn before I let you all lovely people go? I will take that as a no. So all that's left for me to say is thank you so much, Martijn, for coming to speak to us. That was really interesting. I'm sure you guys found that as well. Lots of messages coming up saying great session, thanks. So yeah, we know, good. Good to know. And thank you to all of you for joining us for today's session. And I look forward to seeing you at our next LJC event. Thank you so much for coming. Have a great afternoon, everyone. Take care.
See you later. Bye.
Bye.
All right. Thank you very much.